So in this first question, they want us to do a hypothesis test. We're given a random sample here of size 75. It's coming from a normal distribution. Sample standard deviation S is 22. And then they want us to test sigma equals 20 against sigma greater than 20. So sigma, remember, is the population standard deviation. We're doing the test at the alpha equals 0.01 level of significance. We'll notice first here that we have a random sample that's given right here, and that our sample is coming from a normal population. It's normally distributed. Those are the test requirements. So we want to keep in mind that the test requirements need to be satisfied. So the first question is this hypothesis test left-tailed, right-tailed, or two-tailed? Well, you look at the alternative hypothesis, sigma greater than 20, so greater than goes with a right-tailed. So this is a right-tailed test. And the book should emphasize this more. They don't, but that chi-squared distribution looks like this. It's a skewed distribution. And they call it a right-tailed distribution because if you find the critical value, in this case chi-squared 0.01, that's going to be on the right-hand side of the distribution. And then the area past that critical value is 0.01. And that is the right tail of the distribution. So this looks like sort of a dinosaur's tail if you want. So that's why they call it right-tailed. A left-tailed test, your 0.01 would be on the left-hand side, and two-tailed, you would have it on both sides. So let's go ahead and compute that critical value here. Chi-squared 0.01 means 0.01 area is to the right, and that means 99% of the area is to the left. You can do this with the table. I am going to use the Excel distribution calculator that I provided to you guys. So you open the distribution calculator. You want to look at the inverse chi-squared tab. This will actually be easier than the table. You want to put 0.01 in here for the area, the right area, or the alpha. Your degrees of freedom right here you fill in is n minus 1. So sample size minus 1 is 74, 75 minus 1. And then it'll give you the left-tailed critical value, 48.66, and the right-tailed, 105.2. So if you just update these, so if you update this to 0.05, then notice that your right and left tail critical values update automatically. Change that back to 0.01. So our critical value is 105.20. Just notice here that you divide your alpha by 2 if you're doing a two-tailed test. Okay, so 105.20, that's right here. And that also goes here. So this cutoff is 105.20. And you find your test statistic, and if it's out here, if it's past the 105.20, then it's too extreme to be due to chance, and you're going to reject the null hypothesis. So this region past the critical value is called the rejection region. So you would reject H0 out there. And if your test statistic falls over here, then you don't reject. So let's go ahead and compute the test statistics. So remember, if you're testing standard deviation against a fixed value, your test statistic is sample size minus 1, sample standard deviation squared over the hypothesized standard deviation squared. So our n minus 1, that's going to be 75 minus 1, because our sample size is 75. And we're going to multiply by s squared. Our s right here, 22. So 22 squared. And then we're dividing by sigma 0 squared. This is your sigma 0, the 20 that you're testing against. So we're going to divide by 20 squared. And then you just plug that into your calculator. And if you do, you will get 89.54. And that 89.54 is over here. Okay, it's about right here. Just estimating. But what we know is it's not in the rejection region. So this is our test statistic. So that's our chi-squared test. It's not in the rejection region, so we don't reject. So here you've got a picture of your decision rule. So decision rule here, again, is that if your chi-squared test value, if that's greater than your chi-squared critical, then you would reject H0. And if it's not, if it's less than, then you don't reject. Well, our test statistic chi-squared test is 89.54. That is less than the 105.2, which is our critical value, chi-squared 0.01. So we do not reject. So it could be that this is just due to chance. So state our conclusion. Either there is or is not enough evidence to conclude the population standard deviation is greater than 20. In this case, we did not reject, so there is not enough evidence.